everyone, I'm Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. Today we are going to discuss about certain phenomena exhibited by light, and today we are going to focus mainly on interference phenomena, and we are going to see how this interference phenomena is used in our day-to-day life. So, but before going to this phenomena exhibited by light, first we should be familiar with certain terms related to waves. So, first we should know about these terms: phase difference and path difference between waves. So here, if you can see in the slide, we are considering two waves. Now two waves are propagating, and now I have to consider what is the phase difference between these two waves. Now first we know what exactly is a phase. Suppose I have taken a wave, and in that wave, phase is defined as state of a particle with respect to its position and direction of motion. Suppose if two waves, if they are going in two different directions, then we can say that they may not be in phase. So to be in phase, these two waves, they have to maintain their positions same, and also they should move in the same direction. Then only we can say that they are maintaining phase between two waves. So here we try to explain phase difference between these two waves with respect to this curve taken on time. Here if we say on x-axis we have taken amplitude, we have taken time, on y-axis we have taken amplitude, and when we are trying to find phase difference between these two waves, so how it is given? It is given in this case by the time difference between the same position within the wave cycles of two waves. So here we have two waves. So this red one is one wave which is traveling in this direction, and then we have our blue wave. Now in order to find phase difference, what I have done, I have considered their position with respect to their maximum amplitude, and this difference, it will be the phase difference between the two waves. Here in this case, we are considering the phase difference with respect to time. So if we take a wave, how will define phase of a wave? As I told you, it is the state of a particle with respect to its position and direction of motion. And here in this case, we are trying to find what is the phase difference between the two waves. So we have to compare their positions, and also we have to see with respect to their direction of motion. So when we consider their positions, and here we are taking which factor into consideration? Time factor. So with respect to the time difference with respect to two position on those two waves, then we can define its phase difference. And there is one more way of finding phase difference between the two waves. As you can see in this case, we are finding phase difference in terms of phase angle. So here also I have taken again two waves. This is our first wave and this is our second wave. And if we take these two waves, I'm trying to find what is the phase difference, and here I'm trying to find phase difference with respect to angle. And what we have observed here is with respect to their two positions. If you consider their two positions, you'll observe that these two waves, they are maintaining a phase difference of 90 degrees. So with respect to their positions, so here it has started, first wave it has started from this position, and whereas second wave it has started from this position. So with respect to angle, they are maintaining 90 degrees phase difference. So we can measure phase difference between two waves either in terms of time, or it can be measured in terms of phase angle. So this is how we are going to find phase difference between two waves. And what do we mean by two waves being in phase and two waves being out of phase? Suppose I have taken two waves. If I have two waves, and if I consider their positions, if crest of one wave is matching its position with crest of another wave, and trough of one wave is matching with the trough of another wave, then in this case I can say that these are in phase waves. So these two waves, they are in phase. And when we'll say that two waves, they are out of phase, suppose I have two waves, of course they are moving in the same direction, but here their positions are not matching. Crest of one wave, it is falling on the trough of another wave. So in this case, we can say that these two waves, they are out of phase. And we know that when two waves, when they are in phase, actually their amplitude, it will get increased, resultant amplitude will get increased. Whereas if two waves, they are out of phase, if crust falls on the trough, then what happens here is resultant amplitude will be 0. And there is one more case when we'll say that two waves, they are maintaining constant phase difference. Suppose if you take this example which is given in this figure, so if throughout their motion, if these two waves, if they are maintaining their phase difference 90 degrees, then we can also say that they are maintaining constant phase difference. Now here we have to understand one very important term called as coherence. So when we'll call two waves to be coherent waves, so when we are talking about phenomena related to light, we'll be using this term many times throughout this particular topic. So when we'll say that two waves are coherent, two waves, they are said to be coherent, either they have to maintain zero phase difference. So they have to maintain zero phase difference, or they have to maintain constant phase difference. So if two waves, if they maintain zero phase difference or constant phase difference, then we call such waves to be coherent waves. So here, as you can see in this case, we can say that they are maintaining zero phase difference because their positions are exactly matching. So crust of one wave is exactly falling or exactly matching with the position of crust of another wave. So in this case, we can say that they are maintaining zero phase difference. And when we say that they are maintaining constant phase difference, here in the figure which is given, throughout their motion, if these two waves are moving in such a way that their phase difference is 90 degrees, then we can say that they are maintaining constant phase difference. So in the two cases, we can say that our two waves are coherent waves. And of course, out of phase, as I told you, where the positions are not matching and they are completely out of phase, like they have this difference of 180 degrees where crust of one wave falls on trough of another wave. So this is about the phase difference between two waves. Now next we'll talk about path difference between two waves. Now here I have two waves, and in this case I have taken two sources of light, and these two sources I am calling them as S1 and S2, and I have one wave starting from S1 and it is traveling and it is reaching one point R on the screen, and this screen, it is kept at a certain distance from these two sources. And then I have one more wave which is starting from the source S2 and it is also traveling towards the screen and it is also reaching the same point R. Now I need to find what is the path difference between these two waves. As we have observed here, these two waves, they are traveling from two different sources. And what are those two different sources? One is S1 and another one is S2. But they are reaching same point R on the screen. Now in order to find path difference between these two waves, what we have to do? We have to find difference between the distance traveled by these two waves that are coming from two different sources, but they are reaching same point on the screen. And always what we have to do here is, whenever we are finding path difference, we have to draw a perpendicular. Now in this case, what I have done, I have drawn a perpendicular S1P on S2R. So I have drawn a perpendicular S1P on S2R. Then you will observe that these two waves, S1R and S2R, if you try to find what is their path difference, you will observe that S2R, it has traveled extra path compared to S1R. And what was that extra path? That extra path is nothing but S2P, and this is known as the path difference. So what is path difference? Path difference is difference in their distance traveled. Of course, they may be coming from two different sources, but we have to consider them reaching same point on the screen. So in this case, just we will take distance traveled. And here always, as I told you, we have to draw a perpendicular in order to find path difference. Whereas in phase difference, when we are trying to find between two waves, it is with respect to their position, and that position, it can be measured with respect to time or it can be with respect to phase angle. Now, what is the relation between this phase difference and path difference between two waves? So it is very important relation which we'll be using next in our slides. So if you consider that phase difference, usually it is denoted by phi and sometimes it is denoted by delta, and you will observe that this phase difference, it is equal to 2 pi by lambda times the path difference. So what is the relation between phase difference and path difference? See, once we know the phase difference, we can find path difference between two waves, or it can be vice versa. If we know path difference between two waves, then we can find phase difference. And what is that relation? Phase difference, it is given by 2 pi by lambda times the path difference. And of course, what is the lambda? Well, lambda is the wavelength of light that is traveling, light wave that is traveling. So this is the very important relation which we are going to use further. Now next, we'll come to our phenomena related to light waves. So here we are talking about principle of superposition of waves. So what is principle of superposition of waves? Now, according to this principle of superposition of waves, suppose in a region, in a medium, we have many waves traveling, and if these waves are overlapping with each other, suppose if waves are overlapping with each other, then what happens in that region? Then the resultant displacement in the region of overlapping of these waves, how it is given? It is given as vector sum of individual displacements of each of the waves. To better understand that, we can take example of this figure. In this figure, I have taken two waves, and I am displacement due to first wave, I am calling it as y1, and displacement due to second wave, I am calling it as y2. And these two waves, they are getting superimposed on each other. What do you mean by superimposed? It means that they are overlapping with each other. So what happens if these waves overlap? Then what we'll observe here is, in that region, its resultant displacement will get modified. And how we'll get the resultant displacement? Because of overlapping of these two waves whose displacements are given by y1 and y2, it is given as vector sum of their individual displacements. So if you want to represent it mathematically, as you can see, one wave I am representing with respect to y1, and this y1, it's the function of coordinate x with respect to time t, and then I have another wave whose displacement, it is given by y2, and if these two waves overlap, then the resultant displacement, it is given by y1 plus y2. And one thing what we have to consider here is, we are saying that it's a vector sum. Actually, it's an algebraic sum. If you can see here, net displacement, it is nothing but algebraic sum of the displacements due to each wave. What do you mean by algebraic sum? So it can be y1 plus or minus y2. And when we'll use plus, when these two waves are maintaining phase, when they are in phase. Whereas when we'll use different sign when they are out of phase. Or we can say that if y1 and y2 are traveling in the same direction, and if their positions are matching, if they are in phase with each other, then we'll make use of plus sign. We'll add their displacements. Whereas when we'll take difference, when these two waves, either they are going in opposite directions, or when we consider their positions, if they are out of phase with each other, then we'll take this difference. So what we can say here is, when there are many waves overlapping with each other in a region, then resultant displacement, it is nothing but algebraic sum of the displacement of individual waves. So here we are trying to figure out. So this is our resultant displacement. So this is our resultant displacement, and of course it is given by y. And we have, of course, here two waves. One wave given by displacement y1, other wave given by displacement y2 when they are overlapping. And as you can see, their displacement, and as well as you can observe that their intensity is also going to increase. So this is nothing but principle of superposition of waves. Now we are going to apply this principle of superposition of waves to very important phenomena exhibited by light. And what is that phenomena called as interference? So what is interference? As I told you, interference, it is based on principle of superposition of waves. And here, according to this phenomena of interference, when two or more light waves superimpose, just like we have seen in principle of superposition of waves. And what do you mean by superimposition of waves? When waves are overlapping. So if you consider waves, if they are overlapping like this, then what happens here in the region of superposition, what you will observe here is resultant intensity gets modified. Whereas in principle of superposition of waves, we were talking about displacements. Now here in interference, we will talk about their intensities. Suppose I have one wave whose intensity is given by I1, and of course intensity it is given in terms of amplitude, and we know that intensity it is proportional to square of amplitude. If you know the amplitude of a wave, then we can find its intensity, and that amplitude it depends upon the displacement. So that's why we can say that the interference it is based on principle of superposition of waves. And here, as I am telling, if suppose I have two waves whose intensities are given by I1 and I2, and if these two waves are undergoing superposition, then according to this phenomenon of interference, in the region of superposition, resultant intensity it will get modified. And how it is going to modified? Based on that, we have two types of interference. Or we can also say that there are two types of superposition of waves. And first type of superposition of waves, and on what basis we have these two types? As I told you, it is based on phase difference in superimposing waves. So if these two waves, if they are in phase with each other, then such type of interference it is called as constructive interference. So what is constructive interference? If the two waves which are superimposing with each other, if they are maintaining same phase, then what do you mean by maintaining same phase? If crust due to one wave falls on the crust due to another wave, and intensity of one wave is given by I1 and intensity of other wave is given by I2, then what you will observe here is then resultant intensity it is taken as sum of intensities due to individual waves. And here what happens to resultant intensity? Resultant intensity will be increased and it will give rise to bright fringe. Whereas there is one more interference that is called as destructive interference. And when destructive interference takes place, when your waves are out of phase. What do you mean by out of phase? When crust due to one wave falls on the trough due to another wave. Again, if intensity due to one wave is I1 and intensity due to other wave is I2, then resultant intensity it is given as I1 minus I2. And here, because we are taking difference between intensities due to individual waves, you will observe that our resultant intensity will be very, very minimum and it will give rise to dark fringe. So what you will observe here is based on phase difference between the two waves which are undergoing interference or which are superimposing, we'll have either constructive interference or we have destructive interference. And we try to, here we can better understand it using this particular figure. So what is constructive interference? Again, I have taken two waves where they are in phase with each other, where they are maintaining zero phase difference. Then what happens to their amplitudes? Their amplitudes get added up. It means that their intensities will get added up and our resultant intensity will have bright fringe. Whereas what is destructive interference? As you can see, crust of one wave it is falling on trough of other wave. Then what happens to their intensity? Their intensities will get cancelled and ultimately will have minimum intensity, that is nothing but the zero intensity. So as a result of interference, what we'll get on the screen will get alternate bright and dark fringes. And bright fringes when the waves overlapping are in phase with each other. And when we'll get dark fringe? When the waves which are overlapping are out of phase with each other. So this is about the phenomena of interference. Now, there is one very important concept given by Young's to explain this phenomenon of interference. He has done this experiment, and this experiment it is called as Young's double slit experiment. Now, if we take this Young's double slit experiment, what he has done here is, as I told you, interference. As we have seen in our previous definition of interference, we are saying that waves they have to be in phase and also waves they have to be out of phase in order to get our interference pattern, which consists of dark fringe and bright fringe. Now, see, getting out of phase waves, it's not a difficult thing, but it will be very difficult to have two waves in phase or maintaining constant phase difference with each other. So one very important factor when we consider interference is having waves which are maintaining either zero or constant phase difference between each other. Here we are talking about coherent waves. And as I told you earlier, what are coherent waves? These are the waves, two waves which are maintaining either zero phase difference or they are maintaining constant phase difference. So what do you mean by zero phase difference? When their positions are exactly matching. So this is the example of zero phase difference. And when we say that they are maintaining constant phase difference, when throughout their motion they are maintaining the same phase difference, either it can be in terms of the phase angle or it can be in terms of the time. So such two waves, they are said to be coherent waves. Now, how to get coherent waves? Now, it is very difficult to get two waves coming from two different sources to be incoherent with each other. So here, suppose I have taken two sources S1 and S2. If you see this figure, we have taken two sources S1 and S2. Suppose these two sources, they are completely different from each other. Now what you will observe here is I have one wave coming from source S1. Then I have another wave coming from source S2. And if I make these two waves superimposed, then you will observe that there is no possibility of having constructive interference, or there is no possibility of having phenomena of interference. Why? Because there is one very important point. What we have to understand here is two waves coming from two different sources can never be in phase with each other. This is very important point. So two waves that are coming from two different conventional sources. Here I am not talking about laser sources. Here I am talking about normal conventional sources. And if these two waves are coming from two different sources, they can never be in phase with each other. But in order to have interference pattern, we should have coherent sources. So that's why scientist Thomas Young, he has come out with one solution. What he has done here is he has used a single source of light. So he has used single source of light and he tried to divide the light coming from that source into two parts. And how he is dividing them into two parts? That phenomena, it is called as division of amplitude. So it is called as division of amplitude. So he tried to divide light coming from single source into two parts. And how is he dividing? He is making that light from a single source. Suppose here I have one source. So he is making light from that source to pass through two pinholes. So he is taking two pinholes. And light from a single source, actually monochromatic source which has got single wavelength, it is made to pass through two pinholes, and those two pinholes I am calling them as S1 and S2. And these two pinholes S1 and S2, they will be very close to each other, and usually distance between these two pinholes, it will be maintained as small d. And once your light enters these two pinholes S1 and S2, what you will observe here is your light, it gets divided into two parts. So here I will have, usually suppose I have taken a source and spherical source. If I have taken a spherical source, or we can take one pinhole and we can make light fall on that particular pinhole, then what happens? Out of this source we will have spherical wavefronts coming out, and again these spherical wavefronts, they are made to pass through two pinholes which are kept very close to each other. Then what happens now? Here your light, it will get divided and you'll have waves coming separately from source S1. Now your S1 and S2, they will act as sources of light, but these are not actual sources. Actually they are called as virtual sources of light. And these two sources S1 and S2, what they'll observe here is you will have two different waves or two different wavefronts, spherical wavefronts coming from these two different sources. But because these two spherical wavefronts, they are coming from the same source, so you'll observe that they will be in phase with each other. So here we are making use of the single source and we are making the light waves get divided by making them pass through two different pinholes. So because waves from these two pinholes, they are coming from the same source, they will maintain phase difference, either constant phase difference or zero phase difference. So Young's is able to overcome this problem by making use of this double slit. So that's why this experiment, it is called as Young's double slit experiment. So what is this intention behind using double slit? Because as I told you, light waves, if they are coming from two different sources, they can never be in phase with each other. You cannot expect interference phenomena to take place between waves that are overlapping and which are coming from two different sources. So that's why Young's, he has used a single source of light, and light from that source, it is made to pass through two pinholes so that we can divide the light into two parts, and because this light is coming from the same source, they will be in coherent with each other. Now here we have in this figure, very beautiful figure, which will show you how this constructive and destructive interference will takes place. Now as you can see here, if you take each source, now from this each source, there is one solid line as well as there is dotted line. Suppose if we say that that solid line is crust, if we take it as to be a crust, and if the dotted line, if we consider to be a trough, so like this, we have crust and trough of spherical waves coming from the source S1, and also from source S2 also we have solid line as well as dotted line. It means that we have crust and trough of spherical waves coming from the source S2, and both these spherical waves, they are undergoing superimposition. They are getting overlapped. When they get overlapped, what you will observe here is when solid line or when crust of S1 falls on crust of S2, or when solid line of S1 coincides with solid line of S2, or we can take it as trough of S1 falls on trough of S2, or dotted line of S1 coincides with dotted line of S2, then what happens, as you can see here, is they are in phase with each other, then our resultant intensity will be maximum intensity. Whereas crust of one wave falls on trough of another wave. It means that solid line of S1, if it falls on dotted line of S2, then at those points it will give rise to minimum intensity. That we tried to show in this particular figure. So if you carefully watch this figure, if I go along the center, as you can see, I am considering these points. These are the points which we are considering, and if you observe them carefully, so here if you observe them carefully, you will observe that solid line is meeting with solid line and dotted line is meeting with dotted line. It means that crust is overlapping with crust, trough is overlapping with trough. So that's why what is the resultant pattern that will be recorded on the screen? That is nothing but maximum intensity, and that maximum intensity is nothing but the bright fringe. Whereas if you consider line here, suppose if I am taking this line, and if you see that points on this line, as you can see, if I consider this point, solid line, it is falling on the dotted line. It means that crust of one wave, it is falling on trough of another wave. So similarly, if you consider all the points here, so crust is falling on the trough. Then what will happen? These waves, they are out of phase with each other. Then what you will observe here is their resultant amplitude will be difference of amplitude due to individual waves, and will end up having minimum intensity. And what do you mean by minimum intensity in interference? Minimum intensity means we are talking about zero intensity. So maximum intensity, it will give rise to bright fringe, and minimum intensity, it will give rise to dark fringe. And here on the screen, when we observe, you can see the beautiful phenomena of interference. So here red, whatever red spots or red lines you are able to see, these are all dark fringes, and they are well separated by dark fringes. Okay, so we have red fringes separated by dark fringes, and these red fringes are our bright fringes, which are because of in-phase waves or waves which are coherent, which are maintaining zero or constant phase difference, and they give rise to maximum intensity. So this is the experiment conducted by Young's in order to show the phenomena of interference. And in this case, if I try to close one source, suppose if I am closing one pinhole S1, then you will observe that on the screen you will be not able to see this interference pattern. So this shows that interference pattern will be there only if we have superposition of coherent waves. And we know how to get coherent waves. What we have to do, we have to make these waves coming from the same source get divided into two parts by making them pass through two different pinholes. Now this is one more figure which will better explain this Thomas Young's double slit experiment. So here we are making use of two different colors. In the last case we made use of solid line and dotted line, solid line for crust and dotted line for trough. In this case, as you can see, we are making use of red color as well as yellow color. And here first we have this source. Okay, and actually this source, it is a single slit, and the single slit, it is illuminated by sunlight. Also we can make use of monochromatic light. And here once your light falls on the single slit, out of this single slit you have spherical waves coming out. This is a spherical wavefront. Suppose if red one is crust, then yellow one will be trough. And this spherical wavefront, again it is made to fall on a screen, and that screen consists of two slits. These are our two slits, okay, which are very close to each other. Then what happened from here, you can observe that our spherical wavefront, it is getting divided into two parts. And because these two different spherical wavefronts, they are coming from the same source, so obviously they will be coherent. So they will give rise to interference pattern. Now here I have taken 3 points on the screen. If we take point A, and how this point A is formed, if you consider all those points here, yellow is falling on yellow, red is coinciding with red, and then yellow with yellow, red with red. It means that crust is falling on crust, trough is falling on trough, so it will give rise to maximum intensity. So here you will have bright fringe. Whereas when you go to dark fringe, if you can see yellow is falling on red, it means that crust is falling on trough. So crust of one wave coming from one slit falling on trough of another wave that is coming from the other slit. And here we will have difference of their amplitude, difference of their intensities, and we'll have minimum intensity which will give rise to dark fringe. So this, I think from this we can better understand that overlapping of in-phase waves and out-of-phase waves. So if we try to explain that experiment as I told you, so of course Thomas Young in 1809, he is the first person who is able to give experimental evidence for wave theory of light, and that too by using double slit interference experiment. What he has done here is, he has allowed the monochromatic light to pass through a pinhole, and from that pinhole light it is made to fall on two more pinholes S1 and S2, which are separated by certain distance. And what is the distance of separation? It is given by small d. D is the distance between those two pinholes. And then we are taking one more screen, and where that screen is kept, that screen, it is kept at distance capital D from those two virtual sources. So this distance is nothing but our capital D from those two slits. Now here two slits, they are acting as virtual coherent sources. And what is small d? Small d is distance between these two virtual coherent sources. So we are able to take two very important terms, small d and capital D. And what you will observe here is spherical waves, they get divided by two parts by division of amplitude once they pass through S1 and S2. And now these spherical waves, they will superimpose, and if crust falls on crust, trough falls on trough, amplitude and as well as intensity is maximum, because we know that intensity is square of the amplitude. Whereas if crust of one falls on trough, then it will give rise to minimum intensity. So as a result, we'll have large number of dark and bright bands forming on the screen. So this is about the phenomena of interference, and how Young has explained this phenomena of interference, how he has conducted that first experiment using double slit. So we have seen in our today's video. So we are going to stop our session today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.